All right, well, so as the title slide indicates, this is a talk about interdisciplinarity. So I want to just put a little disclaimer up to start with, which is that I don't have any particular brief either for or against interdisciplinary collaboration. I mean, my PhD, as Patrick mentioned, is in STS, which is an inherently interdisciplinary field. I collaborate with people in management, philosophy, sociology, and obviously I've been a part of this center and its particular brand of interdisciplinarity for a long time. So I certainly think interdisciplinary collaboration can achieve some great things. On the other hand, I do think there's a lot of kind of unexamined interdisciplinarity out there. People just sort of automatically resorting to it as a label for as a label or as an organizing principle to throw together collaborations without thinking particularly clearly about, you know, what is interdisciplinarity? How can you enact it? How should it be structured? What is it supposed to achieve? So what I'm trying to do with this project, or one of the things I'm trying to do with this project, is really take an historical look at a earlier moment when interdisciplinarity was as much, if not more, of a buzzword than it is today, and to see how people enacted interdisciplinarity back then in the late 60s and early 70s, to see what worked, what didn't work, what it was supposed to achieve, what kinds of people it threw together as a sort of imaginary for science and engineering. So to do this, I'm taking Stanford as a case study, and there are many reasons to do that. One is that the Stanford archives are incredibly extensive, so there's lots and lots of great evidence for anything you want to find out as an historian. It's a much richer trove of material than you could get for many other universities. Second reason to look at Stanford is that it's an institution that actively participated in and often drove many of the large-scale changes in American science and technology policy in the post-war period. They were right out at the forefront of the big changes of the Cold War, and then again, many of the big changes of the 80s and 90s. So things you see happening at Stanford are either often illustrative of things happening elsewhere, or they're particular to Stanford, but they tell us something very interesting about science and technology policy in the U.S. And then the third reason to look at Stanford is that there is already a pretty extensive literature in the history of science and technology about this school and the way science and technology were organized there. One of the kind of curiosities that you find, though, if you look at this extensive literature, is that it tends to segregate roughly, I'm exaggerating a bit here, but not that much, into two camps. One is a mostly earlier literature looking at the changes at Stanford in the early Cold War period. Stanford, before World War II, was a pretty sleepy, kind of provincial place that didn't do a lot of research, some, but not anywhere near the level that it achieved in the 50s and 60s. But that changed very, very rapidly in the early Cold War period. Administrators at Stanford really understood what the new funding regime, post-war funding regime, was going to look like earlier than most of their other competitors, and were able to take advantage of it in a way that very few other schools did. And so there's this pretty extensive literature looking at exactly what they did, how they transformed departments, how they steered faculty research, how they grew connections both to local industry and to funding agencies in order to turn this sleepy provincial university into this research powerhouse. And that literature almost all ends in 1970. Most of these books end with the acknowledgement that right around 1969, 1970, something happened that really broke down this early Cold War arrangement. There were riots, there was turmoil, people lost their jobs, the funding dried up. And so one of the themes you get from that, looking at that literature, is that the early Cold War regime wasn't sustainable, that something had to give in the late 60s and early 70s. Then there's this generally more recent literature looking at Stanford as this exemplar of academic entrepreneurialism as this Silicon Valley university, this place with many, many ties to the biotech industry, to the microelectronics industry, to the software industry, to e-commerce, and so forth. And really looking at how that came about, what institutional changes needed to happen, what cultural changes needed to happen in order to get faculty members to patent more of their work, to encourage companies to take out licenses on those patents, to found their own startup companies, to form cooperatives with industry, to just be more engaged with local industry in various high-tech areas. And that literature usually starts either in 1970 with the founding of the Office of Technology Licensing, one of the first university tech transfer offices, or it starts in the mid to late 70s with the Asilomar Conference and the first patents on recombinant DNA and the first biotech startup companies. So this literature really, I mean, it's maybe there'd be a sentence or two about the turmoil in 1969 and 1970, but it really doesn't acknowledge that that would have had any impact on the creation of this academic entrepreneurial mode, right? It's sort of like, well, there was bad stuff in the 70s, but then things got better as Stanford became this more commercial player. So there's a real disconnect between this literature that's kind of ends in 1970 and this literature that begins in 75, 76, 80 or so. And so one of the things I'm trying to do in this project is to figure out what the bridge is. Is there a story we can tell about the collapse of the Cold War university leading to, or at least influencing, the emergence of the entrepreneurial university? Is there something going on around 1970 that can help us understand this transition between these two modes? So what was happening around 1970? Well, lots of stuff. One was that Stanford had a very young age cohort, as did a lot of other universities in this period. And most demographers will tell us that that's a recipe for a certain amount of social unrest. But at Stanford, it was also an opportunity for a certain amount of introspection and reflection about what the university needed to do, what it needed to change going forward from the mid-'60s onward. There was a big survey of Stanford called the Study of Education at Stanford in the mid-'60s that really took note of the fact that the demographics of the student population was about to change radically, was about to become much younger, and set out to try and find out what should Stanford do about this? How should Stanford change to take account of this? And, in the end, this study of education at Stanford was basically ignored by everyone. The administration, when it was finished in the late 60s, the administration had lots of other things on their plate to deal with. Student activists basically said, well, this committee are just stooges for the administration. None of what they say matters. But if you actually go and read their report, you find they summed up the situation pretty accurately. They really reflected a lot of the tendencies that people at all levels of the university, students, faculty, administration, were talking about needed to happen. And the theme they drove home over and over again in their report is that Stanford needs to become more interdisciplinary. Their proposed reforms for curriculum at Stanford, almost all are things like more science courses for non-scientists, more interdisciplinary social science courses, more interdisciplinary humanities courses, more opportunities for undergraduates to take courses in the professional schools, right? So really basically saying what Stanford needs to do in this moment of turmoil, which we know is coming, is for people from different parts of the campus to be more engaged with each other, to have more opportunities to learn each other's way of doing things and to cooperate on projects. Well, as I say, that really got lost in the turmoil, but it's a little bit ironic because that theme really should have resonated, certainly was repeated more or less independently by all sorts of actors at Stanford in this period. The ways it was repeated, though, were often in the context of the real incredible disruption of the campus that happened in 1969, 1970. Repeated burnings of buildings, takeovers of laboratories, picketing of scientists and engineers as they went to work, thefts of classified data, basically disruptions that led to the president of the university losing his job. Just a real sense that this was a university that was becoming ungovernable. And quite a few people, again, students, faculty, and administrators, openly said in this period that this may be an institution that can no longer exist, that its divisions may be so deep that it may not be possible to keep this thing going, that Stanford may actually have to close up shop because of all of the protest and turmoil. So it's important to ask, what did the protesters want? What were they protesting about? Well, some of the things they had on their minds were the obvious issues of crisis of the moment in the late 60s. Issues of race, issues relating to the war, obviously, issues relating to Stanford's relationship or lack of relationship with the communities around it. There was a lot of talk about Stanford needing to accept more students from nearby communities and to do more outreach to local communities. There were lots of protests about nitty-gritty technical matters of university rules. You know, how many students should be on various governing boards? How actively should students have a say in how Stanford operates? But a big part of the protests were about the conduct of science and engineering at Stanford. Many of the protests centered on how science at Stanford should be organized, who should be funding it, what the ultimate aims of that research should be. These were protests that struck deep at the heart of Stanford, right? I mean, you had laboratories being taken over, you had hours-long faculty senate meetings really trying to grapple with the deep issues of who should be funding research and how research should be conducted. This was a real issue of the moment that in some ways paralyzed the campus, right? That people came to an impasse, came to disagreements that really were very difficult to overcome regarding how research should be organized. So, how did the protesters think research should be organized? Well, they were clear that there should be less funding from the Pentagon. Some people entirely wanted defense funding, completely to disappear from campus. Others just said, well, maybe we should get it down to the 10 to 20% level. They wanted no classified research on campus, and there they were actually ended up being quite successful because they could recruit faculty to support them who thought that the idea of a classified dissertation was inimical to academic freedom. And they wanted more applied research, and they wanted more research oriented to civilian problem areas, to the problems of American society that they saw as most relevant at the moment. And those problems were pretty recognizable, again, to students, to faculty, to administrators. This is a list of human problems taken from a letter I found in the archives by a Stanford electrical engineer, but it's a laundry list that you would have found that many people at the time would have found recognizable as the national priorities for science and engineering of the late 60s and early 70s, right? So things like urban problems, mass transit, housing, overpopulation, pollution, medical care, resource limitations, alternative energy, underemployment, and racial strife, right?
Luckily, they're all solved.
Yeah, exactly. So for scientists and engineers at Stanford, on the one hand, they saw their campus falling apart. They saw a significant portion of the student population and quite a few of their own colleagues in the faculty pushing for the solving of these kinds of problems, or at least for research at Stanford to turn more towards the investigation of these kinds of problems. They saw at the federal level that people in Congress and in the various funding agencies were likewise beginning to emphasize these problem areas much more than the areas that had been emphasized in the early Cold War. And at the same time, scientists and engineers could also see enormous budgetary crises confronting them. This was, in many ways, a terrible, terrible time to be an academic scientist or engineer, and an even worse time to be going on to the job market as a scientist or engineer. It was a period of declining federal funding in general, especially declining federal funding for basic research or for research oriented to defense problems. It was a period of terrible, terrible job market conditions for people graduating with degrees in science and engineering. This is a chart that Dave Kaiser made showing the number of PhDs in physics granted in the U.S. But really, you could take this curve and the general shape would be reflected for other things like federal research budgets or job openings in the sciences and engineering. And you see there's a big climb in the 60s when it was good to be in academic science and engineering, and then this precipitous fall off right around 1970, right? So what I'm trying to draw your attention to here is that researchers at Stanford in this period, as at many other schools, faced on the one hand these cultural and legitimacy crises of the university falling apart and pressures to move toward these human problems, and at the same time these budgetary crises of budget shortfalls and rapid and often unstable shifts in where the remaining funding was going to, right? And these were by no means totally separate constraints, right? Obviously, the changes in funding were related to these cultural shifts, but both of them really impinged at the same time and demanded some kind of response, right? So how did scientists and engineers at Stanford confront these many different crises, confronting them in right around 1970? Well, to deal with the budget shortfalls, they realized that they needed to radically diversify their funding, right? People who, through the early Cold War, had gotten most of their research funding from a single military funding agency like the Office of Naval Research, suddenly right around 1970, they're realizing that if they want to keep their labs going, they're going to need to get funding from other agencies. And you see them going out to the National Science Foundation, to the National Institutes of Health, and even to philanthropies and to corporations to fund their research, something that really they had been very loath to do up until the late 60s and early 70s. At the same time, they also became more commercial in their outlook. If you're facing a big budget shortfall, it's not an unreasonable thing to say, well, maybe I should start patenting my research and looking for companies to license those patents and bring some more revenue in both to the university and to my own lab, or even to start a company that would license those patents and make money for myself and my lab and the university. And you see people who through the early Cold War had very little interest in patenting their work and almost no interest in founding startup companies. In the late 60s and early 70s, suddenly they're patenting quite a bit, and in some cases even founding some of the first startup companies of the type that Stanford would really become famous for in the 80s and 90s. What I want to argue is that those kinds of moves to diversify funding streams, to start to adopt a more commercial outlook, those, I don't know if you want to say entailed, but certainly they happened at the same time with, they co-evolved with an increasing urgency for interdisciplinary research, right? Think again, if you're, say, an electrical engineer who has only had Office of Naval Research funding through the early Cold War to do, say, microwave research, and all of a sudden in the late 60s you can see that that money is starting to dry up, and you're going to go look for funding from, say, the National Institutes of Health. Well, you're going to need collaborators in the biomedical sciences if you're going to make a good case for that funding. And so the need to diversify funding streams really co-evolved with a need to find collaborators from across the university, from across the disciplinary spectrum. And what we see at Stanford is this incredible flourishing of interdisciplinary institutions and collaborations right in this period. This is a chart put together by Andrew Nelson showing the number of degree-granting interdisciplinary centers at Stanford throughout the Cold War and beyond. And you can see there's this enormous jump between 1968 and 1969, and then this much, much more rapid growth in the number of interdisciplinary centers in the 20 years after 1969 than in the 20 years leading up to 1969, right? So something happened right around 1969 to make interdisciplinarity this much, much higher priority at Stanford than it had been before. So this project really is trying to unearth the origins of this priority given to interdisciplinarity, but then also to try and parse out the consequences of this very rapid adoption of interdisciplinarity as a new ideal right around 1969. So one thing to note about this chart is obviously there was a certain amount of interdisciplinary collaboration going on before 1969, even if something definitely happened in 1969 to promote more, and I would argue a different kind of interdisciplinarity. So it's important for us to ask, what was the model of interdisciplinarity before 69, and what were the inspirations for the model that was adopted after 1969? And I really see three major strands, both kind of as models in the earlier period and then in a reconfigured way as drivers in the later period. One is corporate research. There'd long been an ideal in the U.S. that research taking place in industry was necessarily interdisciplinary, right? That products very rarely align squarely with disciplinary boundaries. And therefore, if you want to innovate, you need to have teams that are drawn from many different fields. And Steve Shapin goes into that ideal of American corporate research as this interdisciplinary, in this interdisciplinary mode extensively in his book, Scientific Life. And I think you can see a little bit of that in this jump right around 1969. There were a lot of people in Stanford science and engineering departments who had been corporate researchers earlier in their careers, particularly at places like Bell Labs. And in some ways, I think what you see in the late 60s is those people kind of returning to those roots and saying, okay, we know our primary funder, the military, is going to be less dependable in the future. How can we start thinking about our research as a product, and how can we start recruiting, new users, new markets, whether actual markets where you sell the technologies you're making, or markets in a more metaphorical sense where you're trying to get other people to collaborate with you on projects. So corporate research is one mode of interdisciplinarity that I think feeds into this. Second is cybernetics, this field born in World War II and really coming into prominence in the 50s and 60s. A way of thinking about the world as this kind of nested collection of systems that feed back on their own operation, whether you're talking about cells or people or organizations or the universe itself. And as a lot of people have written about, cybernetics from the very beginning was an incredibly interdisciplinary field. It was certainly pushed by physicists and mathematicians, but from the very beginning it had biologists, it had economists, it had philosophers, it had anthropologists. And you see occasional talk in Stanford science and engineering departments in the 50s and 60s about, we need to pay attention to what's going on in cybernetics. But certainly by the late 60s, I think cybernetics becomes a field that people who want to be more interdisciplinary can draw on. And in particular, they can really draw on some of the countercultural interest in cybernetics that begins in the early 60s. People like Robert Rauschenberg and John Cage trying to think about the implications of cybernetics for the humanities and the arts. So that's another strand of thinking about interdisciplinary collaboration. I think by far the most important model of interdisciplinarity at work at Stanford, both in the earlier and in the later period, though, is the large-scale crash research projects of World War II and then of the Cold War, things like the Rad Lab and the Manhattan Project. The person who's usually given credit for creating the Cold War University at Stanford is Frederick Terman, who was the Dean of Engineering and then the provost for most of the 50s and 60s. And he, during the war, had been deeply involved in radar countermeasures work associated with the Rad Lab. He was very deeply connected to science policy discussions going on in D.C. And he took the lesson from World War II, from big projects like the Manhattan Project, that lots of other people did, which is that the best engineering done on these big projects during World War II was done by physicists rather than by people with engineering training. And so the lesson Terman drew from the big projects of World War II was that he needed to go back to Stanford and reorganize engineering so that the engineers would no longer be concentrating on their traditional foci or their traditional methods, but instead would be looking towards physics as a source of ideas, personnel, methods, tools, general outlook. And so you see Terman going back to Stanford, first as Dean of Engineering, and revamping the engineering departments to get rid of things like, goes to the electrical engineering department, and he tries to get them out of power transmission research, saying that's old school. You guys need to be doing solid-state electronics, microwave electronics. You need to be working in areas where you can really be cooperating with the physicists and drawing from their methods and tools. He goes to the metallurgy department, this incredibly ancient empirical field, and he says, you guys need to change your name to materials science. You need to get DARPA funding, and you need to really reorient so that you're borrowing your ideas and tools from physics and chemistry instead of approaching everything in this very empirical trial and error fashion. Then when he became provost, as people like Bill Leslie and Rebecca Lowen and Eric Vettel, who graduated from here, have shown, he did the same thing for the rest of the university. He went to the biology department and said, you guys need to not work on whole animals anymore. You need to be working on genes and enzymes. You need to be working on the elementary particles of biology. And you need to be getting external money the way the physicists are getting external money, right? He went to the political science department and he said, you guys shouldn't be talking about philosophy anymore. You guys need to hire some people trained in computation. And you need to revamp so that you can learn from the methods of the physicists, right? So that's a model of interdisciplinarity, right? But it's definitely a very hierarchical and restrictive kind of model where knowledge flows down from physics and mathematics. The irony, of course, is that the actual projects of World War II and the Cold War didn't really operate that way, right? The people running things like the Manhattan Project or the Apollo Project realized that you needed a less homogenizing form of interdisciplinarity. You needed expertise from lots of different fields to play on a kind of equal field if you were going to get anything done. And I found some great correspondence in the Stanford archives where people at NASA are writing to Stanford and saying, you know, look, you shouldn't be sending us these engineers who are only trained in physics, because the engineers that we need have to make decisions based on economics and law and sociology and management of labor. We need engineers. We need you to train engineers who have the ability to work in all of those different fields, right? So, I mean, the irony of this kind of World War II Cold War model is that what Terman took from it is that interdisciplinarity should be this kind of hierarchical and restrictive thing, whereas the actual big projects of the Cold War seem to have engaged in a more freewheeling and open form of interdisciplinarity. And And what happened at Stanford in the late 60s is that many of the protesters were aware of that. They looked at NASA, they looked at the nuclear weapons program, and they said that we like the methods of that. We like the interdisciplinary collaboration going on in those big projects because it seems to work. We don't like the ends to which it's applied. And so we want to capture, or at least have a say in, the research machinery at Stanford that will retain those methods, retain that wide-ranging interdisciplinarity, but steer it towards the human problems that we think Stanford scientists and engineers should be engaged in, right? So you see a lot of talk from groups like the SDS saying, yeah, interdisciplinarity is great. It's obviously been a priority for NASA, for the Atomic Energy Commission, for the Pentagon, so it must be doing something for them. We just want to apply it to an end other than the creation of this Cold War machine. Okay, so what did this new kind of interdisciplinarity after 1969 look like? Well, it was much less predicated on the sharing of a sort of a single model, right? It was much less predicated on looking toward physics or mathematics, and much more predicated on all fields having some expertise which could be shared. It was much more wide-ranging, right? So the kind of interdisciplinarity you see at Stanford in the 50s and 60s is, social scientists working with each other, people in electrical engineering working with people in material science or physics. Now in the late 60s and early 70s, you see people in electrical engineering working with people in philosophy, in economics, in law, in music, in English. And you see a real celebration of these much more wide-ranging collaborations that involve all of the different schools, that involve the natural and social sciences, the engineering sciences, and the humanities. You see a lot of talk about interdisciplinarity as being a way to heal this campus that's falling apart, right? This idea that, well, if people can work together, they can understand each other's point of views, and then they'll be less likely to burn down each other's buildings or flee to other universities. So you also see a lot of very pragmatic administrative talk about how greater interdisciplinarity is going to save Stanford money because it's going to help them retain younger faculty. It's going to reassure donors that the university isn't falling apart. It may even save on administrative costs because more departments can cooperate with each other, right? So somewhat unrealistic, but at the same time very kind of pragmatic talk about what interdisciplinarity is going to do for Stanford. You also see a lot of much more idealistic talk about interdisciplinarity, how it's going to create students who are more well-rounded, more able to comprehend the issues of the day, more aware of what's going on in their world. And you see applied research and interdisciplinary research really used almost interchangeably. People incessantly talk about how the university needs to become more focused on applications, especially civilian applications, and that necessarily implies that the university needs to become a more interdisciplinary place. You see a lot of people saying, well, the problems of our day are so complex that no single discipline can really tackle them, and so if we're going to move forward, we need to have more cooperation among different kinds of experts. All right. So I want to close by briefly going through 3 case studies that I've been trying to work through in this project and use them to sort of show the arc of this talk about interdisciplinarity at Stanford right around 1970. One project is this device called the Opticon. It was a reading aid for the blind. Basically what you would do is the blind person would stick one hand in this box, and then in the other hand they would have a little scanner which they would run over text, and the scanner would perceive where the ink was on the page, and that would activate a set of pins that were under the blind person's hand, and so they could feel the letters as the scanner moved across the page, right? So it would be a way for them to read text without having to convert the text into Braille, right? Now, this project started in the early 60s. It started well before all of these calls for reconversion and for more civilian-oriented research. And it started partly for personal reasons. The PI, his daughter was blind, and he was really quite focused on technologies that would aid blind people. But the project really didn't go very far in the early days. It was supported at a pretty low level by the Office of Naval Research and by the Air Force, but not a whole lot get done until the late 60s when the PIs found funding from the Federal Office of Education, right? So this is one of the first projects to really start moving toward this more diversified funding model. As they got that funding, as the protests started to set in, as the university realized it was entering this period of crisis, this project became incredibly well known on campus. The administration was very, very active in promoting this as an example of Stanford engineers working on projects of civilian relevance. This was really a way for the administration to say, oh, you protesters have nothing to be unhappy about. We already have people on this campus who are doing the kinds of things that you want them to be doing. So one of the arguments I want to make is that while there were projects of this type going on before the turmoil of the late 60s, that turmoil gave new visibility to these kinds of projects. And that visibility itself made these projects more interdisciplinary, right? So once these projects started to be promoted on campus through things like research expositions and research reports, the project became more interdisciplinary. They were able to attract people from the School of Education, from the psychology department, from the mechanical engineering department, from neuroscience institutes up in San Francisco, right? So the turmoil of the 69-70 led to new visibility for projects that were already somewhat interdisciplinary, but made those projects even more interdisciplinary. Second example I want to point to is called the Center for Computer Research in Music and Acoustics, which is pronounced CARMA, of course. CARMA, lots of people were involved in its founding, but the guy who really mostly pushed it forward was a musician named John Chowning, who partly out of personal predilections, partly from a series of coincidences, became interested in computer and electronic music, became an active member of the artificial intelligence community at Stanford, learned to program, and became a pretty accomplished programmer and inventor. And at the same time, became one of the first real entrepreneurs at Stanford. He he patented a series of his inventions in the 60s and early 70s, and one of those patents was licensed by Yamaha and became Stanford's most lucrative patent in the 70s and 80s. So, this is kind of a underappreciated source of the entrepreneurial university, which we usually think of as coming out of biotech and computing. This is really coming out of music and the arts and humanities. So what I want to point to here is that again, Chowning was doing this work before the really moment of turmoil in 69-70, but that turmoil gave him the opportunity for the collaborations, gave him the administrative support, which enabled him to put together a new center, a new institution. And this, again, we see across Stanford in this period is that this new priority for interdisciplinarity led to the creation of many new organizations. Now, Chowning's career was pretty checkered. He was denied tenure in the early 70s, largely on the basis of one of the classic problems of interdisciplinarity, which is that the musicians couldn't evaluate his work as an engineer, and the engineers couldn't evaluate his work as a musician. And it was really only when Yamaha came to campus and said, we'd like to implement this license on this technology, where's John Chowning, that Stanford said, oh, well, we can give you your job back. Andrew Nelson often uses this. He's working on a whole history of karma. This is an example from the 80s, actually, but it kind of exemplifies the persistence of these interdisciplinary collaborations that were facilitated by karma. This is from a ballet, which is performed by an ensemble including both human dancers and industrial robots. So this is seen as really both an incredibly innovative piece for electronic music and ballet, but also a real spur to innovation in the programming of industrial robots in the mid-'80s, right? So, this is kind of one of the ways that interdisciplinarity can work, right? Which is both all of the contributors to a project can get something out of it, even if it's not exactly what you would expect going in. All right, then the last example is something called the acoustic microscope, which was invented at Stanford in the late 60s by an electrical engineer named Cal Quate. Quate was one of these people who mostly had perhaps exclusively had funding from the military services through the 60s, working on mostly on basic research oriented more or less to signals processing for communication and radar and things like that. In 1966, he and a buddy were sitting around the pool, literally, that's how they describe it, and they came up with this idea of using the technologies they were working on for signals processing to applying them as a microscope to look at biological materials in a new way. But again, much like the Opticon, much like Chowning's work, they didn't really do anything until things really started to fall apart at Stanford. And when things started to fall apart, Quate, to some extent, put aside his signals processing work and really focused on the acoustic microscope and looked quite actively for new sources of funding. He got funding from a philanthropy that dedicated to funding biomedical research. He struggled for a very, very long time to get National Institutes of Health funding, went to the National Science Foundation. He patented the acoustic microscope and got a license from a manufacturer that wanted to make these instruments to sell them to clinicians. So really he was very creative in both in turning his research toward these more civilian projects, but also in making the most out of this project to bring in new funding. Well, it worked and it didn't work. He managed to get lots of samples from biomedical researchers and made some really kind of striking images. But when he went to the National Institutes of Health, they said, well, it's great you got all these samples, but you need to actually work with biomedical researchers. You need to have them in your lab telling you how to interpret this stuff, getting them to understand what it is that's going on in the microscope when it's making these images. And he was not particularly successful at doing that. So what did he do instead? Well, he really responded to the changes in the science funding regime that happened throughout the 1970s. This was a period of very unstable federal priorities in funding, and Quate really seems to have moved from one priority to the next as it came out, right? So as he encounters these problems in forming interdisciplinary collaborations with biomedicine, he realizes, well, maybe we can take advantage of all of the new funding for alternative energy research, and maybe we can apply this thing to understand differences in different coal types, right? So maybe we can use this to find cleaner coal, or at least to discriminate between different types of coal more easily. Works on that for a little while. Then after about 1975, he realizes that there's this huge panic over economic competition in the microelectronics industry. And he says, well, this is a big new priority. There's lots of funding for this, both from the military services and from various civilian agencies. Maybe we should see if the acoustic microscope can be applied to that problem. And so he finds an actual application. Basically, you use the acoustic microscope to look through thin films to see whether a thin film in an integrated circuit has been applied correctly or not. These microscopes are still used for this application today. And what he finds is that collaboration is much, much easier on this project than it had been in the biomedical applications. He's able to get people in the microelectronics industry to adopt this technology, to build their own microscopes, to form a pretty sizable market for manufacturers that want to make these microscopes, whereas he wasn't able to do that when he was working with people in biomedicine. And so what I'm trying to point to here is that even for people who really wanted wide-ranging interdisciplinary collaborations in the early 70s, they ran into real difficulties, and when easier options became available from the mid-70s on, options where they didn't have to get out of their disciplinary comfort zone quite as much, they took those options, right? It was much easier for Quate, an electrical engineer, to work with other electrical engineers than it was for him to work with people in medical schools. He's still working a little bit on biological samples, but not really trying to get biomedical researchers interested in these images. Basically, he's using them as a way to calibrate the microscope because these samples contain very, very small features. And so if the microscope can resolve those small features, he knows it's continuing to improve its resolution. That's not quite the end of the story, though, right? So what happens in the early 80s is that Quate, he's no longer forming these trying to form these deep collaborations with people in biomedicine, but he has changed from the way he was operating in the 50s and 60s. He's now thinking about the object of his research not as a particular application area or a particular phenomenon, but instead he's thinking in terms of a size scale. And in particular, he's thinking of the submicron, or as we would say today, the nanoscale. And saying, well, my lab's expertise is in investigating the submicron world. And so when he hears about this new microscope, the scanning tunneling microscope in 1982, he's instantly hooked. He says, wow, this is great. He gets rid of his acoustic microscope work as fast as he can. He gets into scanning tunneling microscopy. Eventually, he co-invents a successor to this, the atomic force microscope, that's today one of the most important tools in nanotechnology. And in fact, this is kind of difficult to see, but when President Clinton announces the founding of the National Nanotechnology Initiative in 2000, behind him is a micrograph made with an STM that was built by a former Quate student who had taken up STM in the mid-'80s, but that student was not an STM student. He was actually an acoustic microscope student, right? And this backdrop is what the Clinton administration was using as its icon for nanoscale research. So the point I want to leave you with there is to say a lot of these interdisciplinary collaborations of the late 60s and early 70s didn't work, or they didn't work as well as people had hoped at the beginning, or they just turned out to be a lot harder than people thought. And in many cases, people turned away from those kinds of collaborations from the mid-70s onward. But the next time there was a moment like 1970, and that was after the end of the Cold War, the next time people came around saying, well, We should convert a lot of military-funded research into civilian-funded research. Many of those people who had tried to make these changes in the early 70s were the ones who were able to take advantage of those new changes after 1990, and the way they were able to implement those changes in a more viable way, the way they were able to enact interdisciplinarity in a more sustainable way was by putting it under the umbrella of nanotechnology. Nanotechnology provided this sort of organizing principle for more sustainable interdisciplinary collaboration than they had been able to achieve in the 1970s. So, thanks.
Cyrus, I have kind of some detailed things, but sort of a larger framework question at the beginning. It sounds to me like you're arguing there were essentially converging drivers from two unrelated groups, at least as we normally think of them as left-wing protesters, largely students, mostly younger but not only, who are opposed to the defense orientation of funding, among other things, and want to convert military research into civilian research for human needs. That's the slide you put up. And the second group are essentially older people, scientists, science policy people, federal funders, who are for reasons which are kind of weird, actually,